you to do this? Okay. Yeah. Pretty big one.
What?
Pretty big.
You see it's petals.
That's what?
It's shiny.
Oh, weird. I didn't know they added that.
It's
I have
cool.
a shiny swallow.
I don't have that game anymore.
I never had it.
Yeah, it's good.
You're always cool.
I also have a Pikachu that wears sunglasses and a hat.
That one, that's a shiny one. It's not really yellow.
Yeah, right now. It's
You gotta get the shiny Rayquaza, otherwise it's not cool. Black.
Our legendaries are really, yeah. They're the teaching Charizard.
Black and blue. Yes. Well, the original shiny Charizard was black with blue.
Yeah.
So is there a
And
new
then
one?
they made like the negative edition. But no, I haven't done legendaries that much. There's a couple of photos. Until we go there.
Well, let's wait until these things will come up, and I am impressed with your dedication to the class that you start celebrating Labor Day here instead of departing somewhere. So some of you did express interest to the syllabus by your request. I don't know who and why needs it, but if you care, there is one.
Oh, thanks.
So many people start grilling and fireplace during the Labor Day. And when you do grill, you need to have some kindling for your fire. So I will provide a lot of printed materials so that even if you do not read them, you have at least something to kindle your grill. So there will be several handouts, and it's time. I'm not yet ready to entertain you with a homework, which probably you are missing so much.
No chance.
But there will be a way to show your knowledge accumulated in this class and brag with it here. So let me suggest, announce, and administer the oral presentations in 1 week. So there will be material presented today, briefly on Wednesday, and then by Friday we'll split some material between everyone in class, and you'll just come and briefly mumble something. Okay? So probably this is most interesting part. So let me. I'll start with this. So there is a list of names. There is a list of subjects that I will explain what they are, and you have a copy for your memory that you take with me, and I will probably put some symbol. Want to share something on the computer. So there will be one copy star that during the class you pass it around, and by the end of today's meeting I will collect it and have it as a record. There are less subjects than people in the class, but there could be team presentations or and you can, if there is more than one volunteer for a subject, it's fine. If there will be subjects with no volunteers, I will redistribute, but if it is not needed, we will do pure democracy.
So, oh,
This is just pass around. So the subject for the presentation is the postulates of quantum mechanics, and this is on one hand one of the most important parts of the course, and on the other hand it is one of the most boring. So that I don't want to present myself, I'll let you do. Here is the answers to these questions. So it is about 2 pages with answer on what one can tell about each of these 1, 2, 3, 4, 5, 6. But this is too short. If you show just this, we can be done in 10 minutes. You can look around for whatever Wikipedia or just browse internet and share your vision. The benefits of doing it is that we will have the free communication. You share your own thoughts, and it will be less boring compared to if I would be presenting and inviting you to memorize something. So if you have a live discussion, it will be much better. And in some sense, this subject summarizes what we were discussing up now and what we will be discussing next meeting. Yes, yes. Okay. So I'll finish distributing materials. So that, because then you all will get excited and go through slides, and there will be no time to distribute stuff. So there are a couple of more handouts, and they are most of them are prefaces to the textbooks for the subject. And those are prefaces not to the recent learning textbooks. They are prefaces to original books of the developers of the theory. So they share their background thoughts that are not typically studied, but it is a logical way that brought them to the idea to develop this and that equation. And you know that math is just language of chemistry and physics. And if you read background ideas of the developers of the theory, you feel a little bit more comfortable rather than just digesting boring equations. So the first preface is from the collection of papers by Schrödinger. So we are studying Schrödinger equation, and there are a couple of words where he expresses his views. So how he came up with an idea to write an equation and what was the philosophical background. This all is optional. If you are lazy to read or bored to read, I don't care, but maybe it will be an interesting compliment to what we do in class. The second one is a preface, and you know, today I'm distributing materials only developed by Nobel Prize holders. So it is something that was already accepted by community as something valuable. So the second one will be preface from quantum textbook of Leo Landau, who also got Nobel Prize for some cool stuff in a literal sense, like super cool helium. And his book is very boring, and many people do not like it. But it is a summary of many things, and at the beginning, it is much more human. So it is ideas rather than equations, and right? So it is very similar to what is in the preface by Schrödinger, and you see connections to the ideas of waves and wave action principle and the accumulation of phase along the trajectory, but not from my pathetic mumbling, but from the point of view of well accepted people. And another Nobel Prize holder, Richard Feynman, who wrote, I don't know about his scientific achievement, well, I know. Some people do not know about his scientific achievements, but much more intrigued by his popular science books and collection of scientific jokes. If you ever walk to the library or bookstore, you may run into a collection of jokes by Feynman more frequently than to his scientific works. And in the, this is not preface, but it is undergraduate textbook, well, for physics majors, but it is for freshmen. So it is background for quantum mechanics equations, and it also not so intense in equations, and it relates to what we do in class. Well, the thing that I guarantee that if you start fireplace or grill on the Labor Day, you will be not short in kindling. The last thing is not from the Nobel Prize holder, it is from one of the textbooks for chemists. And I will refer, it just shows a table of some notations that I will refer to at the last minute of the class. So from this table, we will some sort depart from philosophical background and go to actual part of physical chemistry where one tries to convert concepts into language of equations. So this is distribution of the postulates that you will present in a short and form. Here is the form that I hope you will complete and put your names in. And when we were starting our meeting last time, we started with this table, and we got acquainted with Euler equation is very approximate. It's not a equation to solve real problems. It is more philosophical. Wave function is proportional to exponential with action playing the role of a phase. And then we did formulated a goal to predict future in a scientific sense for some micro object. basically future of light, not of the universe. And future means that you start from wave function at initial time and you obtain wave function at final time, where the conversion from the past to the future can be expressed in terms of this yellow box, which is evolution operator, which is same as analog projection, something like the dimension of energy times time in the power. We also briefly went through the interpretation of the wave function, which has two interpretations. One is a probability distribution we find in a specific location of space and time, and another one that is a density of charge. So the first one is good to declare in public, and second one is just as an illustration for yourself. If you are on an exam taken by some other instructor, and but we stay with the goal of predicting future. There are several ways to predict the future. To work with the wave function, which always need to be taken square to get the probability. And we are developing a mathematical equation to see how this distribution of probability develops in space and in time. There will be several approaches to make this prediction of the future. So this one will be called evolution operator, because it's evolution not in the sense of Charles Darwin, but in the sense of just propagating forward in time, evolving from past to the future. This is Schrödinger equation for which Ernst Schrödinger got his Nobel Prize. And, we are going to kind of derive, or at least show where this equation comes from, assuming that no one objected and everyone accepted this evolution of rules. From this equation, and another thing that we need to do before we depart to celebrate long weekend is to chat a little bit about quantum operators and their pleasant or unpleasant features. So don't worry, there are no homeworks, nothing scary, but with all we need to get into the loop of thinking about this stuff, which is originally looks counterintuitive, but when you come to analyzing real problems, it seems the only way to do it. So, this is what we also talked last time. So we go from past to the future, and it is an exponential with summation of energy times time at each little sub-interval, right? So there is no matter whether we consider it as a summation of energy times progression here, or if you break this exponential as a sequence of little evolution operators at each little time step, because you know the exponential of a sum is product of exponential. Give me a little hint if it bothers you. Right. Good. Okay. Now I'm going to new material. So everything that no one protested and objected becomes accepted truth. So from now on, the way of predicting futures through evolution operator is the truth accepted by the class. So you can use it as a cornerstone and depart from it. So before we are going to solve two real problems in the little spot presentations, we will come to two problems that will be very important. So So here we can call t sub 0 as initial and t without 0 as past, the future. And we are departing from t sub 0 to t. And then it will be evolution at the interval from t0 to t. So this difference between these times is there. In some sense, it is an equation for wave function. So all philosophy of quantum theory of these electrons as a waves is already there. There is no philosophical problems. One also can formulate an energy objective. The only problem with this equation that it is extremely unpractical for solving real problems. It is like maybe 1% of 1% of, or even smaller, 10 to the power minus 6 of true problems are solved by this equation. Because products is not what computers and people like. Summation is much easier. So can we convert this equation in something that is easier on mathematical sense, that you have less products, more summations, and probably you have no exponential to the power of energy. Much simpler if you have like energy multiplied by to such form. Our tool, then our tools for predicting future will be more applicable to this. So I am going to offer you a little mathematical experiment. So the experiment will be, how does this equation respond to time derivative? So what will happen if you take left and right part, if you take time derivative left and right part? How do you take derivatives of products? Huh?
Product rule.
Yes. Anyone objects against product rule? Okay. So you take, if your function is product of function 1 and function 2, then your product rule will be derivative of first function times second unchanged plus first unchanged times derivative of second. Okay. So what is our first function? What is our second function? First function will be evolution operator, and second will be initial wave function. You have all this stuff in slides, but it will be boring. So we have u times here should be u times here plus u times t. Right? So we are taking derivative over time, but our initial time, our past, is constant. We just intuitively, we do not have power to change past. Although there is a lot of science fiction, but there is no practical tools for time machine and changing the in the past. So because of this hand-waving argument, derivative over past, because we do not have time machines. I don't know. Then it will be only one term. So derivative of the evolution operator times wave function of the past. So we need to just take the derivative of the evolution operator. So e to the power minus h5. And if this was very short, well, formally it should be integral, but if our time interval t minus t0 is very close to 0, small t. Then we can just h times t, okay? Or whatever, delta t equal So how do we take derivatives of exponentials or any functions wrapped into each other? Complicated function that is a function of the function. You take derivative of the outside layer function. How do you call it?
Chain rule.
Chain rule, yes. Okay, I'll skip it this time, but it will be a really nice time for someone to volunteer and complete. So chain rule. So we take first we take derivative of exponential, and then later derivative of the whatever is argument exponential. So what is derivative of exponential? It is whatever it was, exponential itself, right? So we keep this e to the power I to the power h times derivative of this argument. T of is minus I h power h t minus t. So what will be the derivative of this thing which depends on time just linearly? What is derivative of t? D over dt of the function equals t.
1.
Yes. What will be derivative of constant times t?
Constant.
Okay, so here is our constant. So, and this term is equal to our original u. Minus times h times yeah, that's it. And here, when we were taking derivative of our right side equation, we also had the wave function of the past. So as a result, we will have this combination of evolution operator, factor, Hamiltonian operator, and wave function of the past. Okay? There is nothing interesting, just the same question. So d dt u times 0 equals minus h bar h u times size, or let's be specific, time t. So there is a very little intellectual effort to come to success function. If you look back onto our definitions, then influence of the evolution operator on the wave function of the past will be our to the side, right? So we can tell that time derivative t of wave function f times t equals this stuff, then it equals minus I over h bar h times sine of t. Okay? this is really big advance. You did a major breakthrough. I'm not telling that the rest of the course will be super easy, but right now, like if you play RPG, computer games, you got your strongest weapon. So this equation that will help you to fight any problem. And there are benefits. So on the left side, you have time derivative of wave function, and on the right side, you have Hamiltonian operator times the same wave function. So the benefits. Before, our equations were non-local. They were developed for wave functions formulated at very far past, very far future. And mathematically, anything that is non-local is a big disaster. This one operates only with local derivative, which means like infinitesimal increment to a very narrow future. And it refers to wave functions at the same time. So we are local in time. It is really cool. This one benefit. Another benefit that we do not see, there are no exponentials, just products. So we just need to come to agreement how we formulate this energy operator, and then we can go forward and solve any problem. Well, with some limitations. Yes?
So you're saying the highlighted portion on the bottom equals the green portion right above? Is that what the...
Yes.
Okay.
Yes. So from now on, you are holders of this weapon. You are advanced users of Schrödinger equation. CHEM364. Okay, so imagine the O with two dots on the top is red like there. So if you want to speak with Germans, Schrödinger. Yeah, and it is basically the same what we did, just a little better colored. Okay, what else? Oh, this is time-dependent Schrödinger equation because it shows propagation in time. Later on, some poor kids who study physical chemistry and quantum theory in other colleges, some people shorten the courses so much that people just do not get exposed to time-dependent Schrödinger equation, and give it's much simpler object, so-called time-independent, which is also fine to solve some very basic problems, but you are going to the big life with tight hands. So this one is more powerful and more general. This really will help you to do many things. Okay. Now, laziness is the main drive of human progress. There is nothing wrong to be lazy. Otherwise, how would humankind design new technologies, new instruments that make our life easier? So, math is really cool, but since neither one of us went to math department, we probably are not looking towards the career of mathematicians. But for practical reasons, there will be. This course will offer us challenges, mathematical challenges that need to be solved. So, is there a way to solve mathematical problems without diving deep into them? Here. Right. So we want to solve equations of quantum theory by computers. And we can reformulate Schrödinger equation in the finite differences form that can be solved by a computer. So we can next 10 minutes I will tell nothing new. I will just look on the time-dependent Schrodinger equation from slightly different angle, the angle of a robot. So the angle which will help to solve it numerically if we decide to do it one day. So on the left hand we have time derivative, which is psi t plus delta t minus psi t divided by delta t, right? It is your favorite equation from calculus, definition of derivative, right? And it was our left part. And this is equal to minus part dash capital psi of t. So what we can do? We can forget about this rigorosity. Just assume. Then we can multiply left and right part of equations by time. And then we can take this wave function in the near past to convert it, transfer it from left to the right side. When you transfer something from the left to the right, it swaps the sign. Right? Well, I wouldn't brag that is a best possible calligraphy to compete on the tournaments, but probably you still can read it. So this top part is, so to say, left side, and this bottom is, so to say, right side. So future, near future, psi of t plus delta t equals the near past psi of t minus this constant operator times near past times delta t. So we have reformulated Schrodinger equation into the form that is ready to go to predict near future. So we do have past on the left, and we have future on the right. In this infinitism, this finite differences, delta t increments, is what computers are so strong. Okay? So if you enjoy programming, you know how it goes. You just set a procedure and then you repeat it again. You let it computer to look over it and go over it again and again. Right? So you prepare far past. You set a procedure that propagates from past to the future by this time increment. You go through it, predict small step forward. Then you return to the beginning of the loop, apply this protocol procedure once again, make another small step to the future. And then just increment a little bit forward and forward. And then you have solution at each point of time. We will return to this idea a couple of times in the course, especially in the Wednesday labs, when we will use computers instead of brains to solve the problems that we will formulate. Well, things do not change from year to year with the same equation from previous time. So we do have several ways to predict future. We have very general but useless, not practical, evolution operator technique. We do have general and used in 99% time-dependent Schrodinger equation that probably all of us will be able to reproduce with closed eyes very soon. Just time derivative equals to minus constants imaginary unit over h bar times commutative. It's not a big deal to memorize. And the third way is Schrödinger equation for orbits. So the formulation of Schrödinger equation in the time increments. So this is past, this is future. By the way, we can put the wave function for the past out of brackets, right? So psi times 1 will be psi. This out of bracket. And this portion, in some sense, it is also an evolution operator for infinitesimal small time. If you are indeed big, if you love math, you can come to this equation right away by Taylor expansion of the E minus 5 h bar h over t. If you recall the Taylor expansion, then it will be 1 plus whatever we have here to the first power of the argument plus this stuff squared over 2 factorial and the squared. So it is giving terms in the Taylor expansion of evolution theory. It's fine if you don't. So, generous 9 minutes left, and we have one more thing to get acquainted with. What is HM? How do you formulate it if you solve practical problems? So the H capital is operator of energy, right? And you can background your formulation H operator based on classical mechanics. But if you know, for example, that kinetic energy is mass times velocity squared over 2, or in other way it is, what's the kinetic energy?
Half mv squared.
Huh?
1/2.
That's right. And there is another form, it's for momentum. Then you know your number. Like p squared over 2.
Square over 2m?
Yeah, p squared over 2m, right. So then you need to define what is momentum of flow. If it would be a point in space, we would be able to define momentum. But since it is a distributed stuff, we replace, so we use same prescriptions for energy, like kinetic, potential energy, as we would do without quantum in old-fashioned classical style. But now we replace each classical variable into quantum operator. If you're taking notes, you may afford it, or it's probably written somewhere too. So this table shows the replacement of classical variables into quantum operators. So the main, simplest and main thing is that momentum is replaced by derivative over space, which looks a little crazy. But we will discuss and digest this idea again and again. So if you never plan to do any physical chemistry calculations, if you like stop the class, okay, you just memorize. Classical variables are replaced by quantum operators from given table. This is correct, but in order to master this skill, we need to discuss more in class. So when we depart from old-fashioned classical mechanics to these quantum operators, there appear both benefits and complications. So variable is just whatever, a number or vector of 3 numbers. Operator is a stuff that acts on the wave function that is distributed in space and time. The feature that I invite you to look at right away is so-called commutation. So you will come up to it again and again. Commutation is not communication, although it starts similarly. Many people write, let's consider quantum communication. Commutation means swapping order. So if you have classical variables and you have some equation, useful equation, and they are in the, there is a multiplication of several variables. You can swap them without any penalty. Right? 2 times 1 equals 1 times 2. So x times y equals y times x. If you go into the quantum world, it is not more. If you want to swap orders of things in a product, you need to pay. This is a very counterintuitive thing. And if you get through this idea, then you will be like 2 swords. One is Schrödinger equation, another quantum operators. So let me give an example. So for the sake of time, probably used already available stuff. So if you have constant multiplied by wave function, then wave function multiplied by constant, it is fine, right? We can multiply 1 by wave function, it is wave function. But what if we apply derivative operator that acts from left to the right, and we swap order of wave function and derivative? If derivative is in front of operator, it changes wave function. If it is after, it doesn't change. It changes only things that after it. And we can further develop this idea by applying derivative operator to the product of wave function. Well, we are departing from dependence on time and look only how it is distributed in space, because we cannot do everything at once. So wave function depending on the position multiplied by position. So let's just make mathematical experiment and apply derivative to this dx x times product rule, right? So dx x times wave function changed plus x minus d wave function derivative. What is derivative of x dx? Yes. So we're getting wave function plus x plus d. Now let's compare left and right side, or maybe just part to the left. Dx over x times y minus x times 5 equals 5. So you see that here we apply 2 operators. Like any function or set of derivatives can be mathematically called operator. So here operator of derivative and operator of position. And here operator of positions times operator of derivative. So we swap their order, and as a penalty, there is it is non-zero. If you would have like 1 times 2 minus 2 times 1 will be 0. And here it is not 0. Right? You're convinced from this example. And this happens again and again. And many laws of nature are derived from this commutation relations. So just giving you heads up to look in it again and again. Okay. Well, some people, this relation will be correct independent of what actual wave function is. Therefore, we can remove wave function from consideration. We can just cancel it and tell that operator of derivative times position minus position times operator of derivative equals 1, in the sense that it is operator. And some people, if you have A and B minus B times A, they put it in a square brackets and call commutators. Okay? You have seen this table, which projects this. So this is things that we will focus at original steps, but if one goes to more complicated, we'll table. And meeting is complete. I'll stay here to answer any questions. Otherwise, have a pleasant celebration of long Labor Day weekend. I am looking forward to collect your volunteering wishes. Okay. So the PowerPoints with your presentations are expected on Thursday midnight, the night before presentation.
Could you go back like 3 or 4 slides to where you were talking about commutation? So why does the ddx times x minus x ddx equal 1?
Well, this is not one like number. This one more in sense of operator, and
It's just a placeholder for a non-zero number.
yes. I think that we have agreed on. So if there is a function after operator, then it will be correct mathematical expression.
Okay, that's fine.
And now we can generalize it and tell we don't care what will be the function. Any mathematical function will give the same relation. Therefore, we just cancel this phi everywhere and just tell that it is basic property of the operators. That you swap them will get 1. Which means if you have function after each of these operators, you will get the function here.
Okay. I still don't understand why if you do the commutative property, why it equals 1.
Well, it is not for, it's only for this particular example, for these 2 operators. Their commutation will be equal to 1. 2 other operators.
Sure. Okay.
So it's not, you cannot tell the commutation of any operators.
Okay. But if you do a commutation and do it like this, it will not equal 0. Like
Very often, there is no promise, there is no theorem that commutation of any operator will equal 0. Sometimes it is 0, but very often it is not.
okay.
And we just need to stay alert and always check.
Okay. Right, so this will equal 1 and this will equal 0. Supposedly, is that how you would get the 1?
Well,
Yeah.
if you
But yeah, I gotta head out.
understand
So
and imagine,
you have a good weekend.
those are operators that act on a function.
Okay.
So when we go to the next slide where phi is diluted, it is abstract. It is you cannot just use it practically. It is abstract thing that prompts us what would happen if these operators would act on some arbitrary function.
Okay.
So are we giving a presentation on our postulate? Is that what we're doing?
Mhm.
next week?
Yes.
So we have to research the postulate and then presentation about what it is.
Yes.
How it works.
Yes.
Okay.
Where do you want that turned in? Like, you want it turned in online somewhere?
Just send me emails with PowerPoint by Thursday night, and it's just to have things organized. If someone is still awake and has a fixed morning, there will be no punishment. But you know, technology not always works.
Yeah.
If I upload everything at once and you just come up to the ready presentation, it will save us time.
Yep.
And although it is a simple subject, I have no doubt that you find things and make nice presentations. There is so big danger to fall into long speaking mode. So most of you, even involuntarily, will try to override your time limits. And my main goal for the next Friday will be to break the time is over, give the floor to the next people.
How much time are you gonna take?
50 minutes divided by a number.
So it's just a brief description. Oh,
Yes, it's like 3 slides with the
Oh, okay. I was like 10 slides in my head.
Well, you can do 10 slides, but then you film the first film, second film, stuff.
I gotta practice actually.
If we sign up for the same postulate, can we present together?
Yes, team presentation. You know, like news. Good morning, ladies and gentlemen. It's like, here are our postulates.
Okay, thank you.
Oh, Professor, are these readings based off of content we've gone over past week?
They are complementary. They are related.
Oh, okay.
So it's if you do not read any of those, I don't mind. It is just a way to complement, and you see second opinion. Like I was trying to deliver similar concepts, but those people are developers of theories that I'm presenting, and they may have better language or more precise description of what are the fundamentals of these theories.
Okay.